Welcome to Peninsula Seniors Out and About. Today we're at the Western Museum of Flight in Torrance for one of their celebrity lectures. Let's go see what Cindy has for us today.
Welcome everyone to the Western Museum of Flight. I'm Cindy Maka, the director. All too often, when we encounter an interesting subject and would like to know more about it, we have to rely on official records, historical accounts, and other second-hand sources. But once in a while we get lucky. We find an interesting subject that we want to know more about, and we are able to get first-hand accounts of the inside story. Today is one of those lucky days. We have found two old hands who are well equipped to provide us with first-hand insights. What's more, when it comes to knowledgeable old hands, they don't get much handier than these two. And let's face it, they don't get much older either. So, ladies and gentlemen, I have the privilege to introduce two of the best old hands in the business, Ron Gibb and Roy Martin.
This is a rare opportunity to document a development of reconnaissance in the F-5. I was hired in 1966 to support the first camera installation on F-5 and ended up being involved in every version of the reconnaissance F-5s. And then it was also the project engineer on the RF-5E. And it was a 32-year program. I'm going to talk about the history and the design, and then Roy's going to talk about what really happened after they got to fly it. The discussion subjects are a little background. The early reconnaissance in the F-5A, which the RF and the Canadian and the F-5E, the influence that we had on Vietnam, on the design and decisions on the RF-5E, and then the Northrop-funded demo and full-scale production, the Saudi program with the LORAP, Singapore co-production, and then we did a GPS upgrade in Saudi in the late 90s. Then Roy's going to talk about the flight test operations for all of this activity. For those of you that may not be familiar with the F-5T-38, if you look at the family map, there were 31 major variants that Northrop produced, starting with the N-156F, which was going to be a lightweight fighter for the Navy Jeep carriers, which then converted into the T-38, the F-5A and the F-5B, and then the E and the F, and then the RF versions of that, and then the F-5G and F-20. So there were quite a few variants over the years. Northrop was involved in 3,800 aircraft, roughly 1,200 T-38s, 1,200 F-5As and Bs, and 1,400 Es and Fs. In that, there were 107 RF-5s and 12 RF-5Es in production, and then the Canadians had 25 noses, Saudi had 20 noses, and then Singapore converted 15 aircraft after production for a total of 3,800. The production lasted 30 months. The peak production was 27 a month, which was pretty substantial, a lot of aluminum going out of Hawthorne. 38 countries have operated the F-5 and T-38, and right now there's still 24 countries flying the aircraft, with the Air Force going to fly the T-38 to at least 2035, and the Navy probably to 2035 also. Looking at the roadmap of the reconnaissance aircraft, starting with the F-5A, we had a camera installation on one Scotia Tiger aircraft in 1966. We started the RF-5A and the CF-5A about the same time, resulting in unique configurations for Norway, Spain, and Turkey. Spain co-produced 18 aircraft. And then the Saudis had a small system like the RF-5A before we went to the RF-5E, the first one being Malaysia, and then Saudi, Singapore, and Taiwan. There were a total of 196 aircraft that had recon capability. This is my favorite shot. This is a picture of the first production aircraft over Edwards, the T-38, and then the last production aircraft, which was a Saudi RF-5E LORAP flown by Roy Martin. And it turned out that this RF-5E was the last production dedicated reconnaissance aircraft that was built. Let me just talk briefly about requirements. You're going to hear a lot about resolution. You need good resolution in the lens and the film. You need to be able to take pictures in stereo, and what you do is you take pictures with a 56% overlap in space, and that happens to be the same overlap as your eyes, so you can look at two adjacent negatives in stereo and take measurements in depth. Because of the high velocity of jet aircraft, targets are going by pretty fast, and so most of the sensors had forward motion compensation, which negated the motion of the aircraft by either moving the lens or the film during the shutter speed. And then lenses do not like temperature gradients, so that's always an issue. Windows want to fog up when you go from cold altitude down to the deck. And then with film systems, it's not like the EO today. You're always fighting low light levels trying to get imagery. The challenges the designer had was you had to handle that aircraft velocity and motion, rotation, and vibration. You had to deal with the temperature gradients. You had to integrate the sensor. Atmosphere quality completely dictated what you could do. A bad day, you would not get very good imagery. And then low light levels was something you had to handle. Now, just a brief technical discussion on resolution. Air Force resolution is measured in line pairs per millimeter on the film. And they use the same targets as lens designers use on an optical bench, except these targets are on the ground and they're a lot bigger than a few inches. This target here that you see is 80 feet by 120. It's on the range at Edwards, which is 13 miles long, and there's 31 resolution targets on that range to allow the aircraft to fly down and get a lot of data all in one pass. Now, how do you measure the resolution? You look at the negative and you keep going down smaller and smaller until you find one element of bars where the space disappears, and that's your limiting resolution. Now, most cameras and aircraft in the 60s had a resolution capability in flight of about 25 and 30. But what's 20 line pairs per millimeter? It's 20 bars and 20 spaces in 1 millimeter. That's 40 units. 1 millimeter is 40 thousandths of an inch, and so that bar on the negative is 1,000th of an inch wide. So you're looking with microscopes to be able to measure that. When you get to 60 line pairs per millimeter, that's 3 10,000ths of an inch wide. And the rule of thumb was for every resolution element that you needed, 60 line pairs required a 60 power microscope to see it. Now, going into the early reconnaissance, the Scotia, we installed a panoramic camera in the nose of an F-5. They had a 180-degree scan. And the idea was, the Air Force said, well, each attacking target, if we could record the approach, the bomb drop, and the impact, then we wouldn't have to send a reconnaissance aircraft back to record the bomb damage assessment. It was a great idea, except they didn't talk to the pilots. The minute that bomb release occurred, the pilots were yanking and turning, and most of the time the cameras were pointing toward the horizon. It wasn't a very good flight evaluation in Vietnam, and then they dropped the program. On the RF-5E, you had all these countries around the Iron Curtain, quite a few F-5s. The Air Force said we need to provide them with a reconnaissance capability, so they directed Northrop to put a recon system on the aircraft. But because the aircraft was so small, we could not use the standard Air Force format, which was 5-inch film. And so we went to a small strike tactical reconnaissance 70 millimeter that was being used in NATO. And we made a casting 4 feet long that was in the very tip of the nose. And the problem was there were not very many 70 millimeter reconnaissance cameras. Most of them were all 12-inch or 5-inch. And so the Air Force said, well, we'll go buy the camera and we'll provide it to you, GFE, and we'll control it, but you still have to meet a guarantee. And that guarantee was we had to resolve a 6-inch object at 500 feet at Mach 0.8, which is 26 line pairs per millimeter. And you have to do that on 80% of all the data you collect. And we said, yes, we could do that. This is a picture of the nose. It was 2 castings in a clamshell design with 4 cameras in it, 4 feet long on the very tip. Now, there were 3 aircraft systems that used this nose. The first one was the RF-5E with a J.A. Maurer camera, a KS-92. The CF-5 in Canada used a Vitten NATO camera. And then the F-5E Saudis in their first aircraft used KS-121 camera. All cameras systems used 3 different lenses, a 100-foot magazine, a 70mm film, 6 to 8 cycles per second, which was pretty fast, and either a 3,000th or 4,000th of a second shutter speed. And then multiple arrangements which allow you to take 3 cameras and look horizon to horizon to get a full array. The RFI program started in 1967, early 67. The first flight was in May of 68, and the whole flight test program was completed in 68 also, August, with the first aircraft in country in 1968. There were 123 aircraft that ended up in 10 countries, with the largest user being Turkey. They got 20 production aircraft from Northrop, and then they converted 16 aircraft in country. This is the first delivery that went to Iran. In the cockpit is Lou Nelson, who did the first flight. This picture of the RF-5A with the forward oblique window and the Coke bottle effect. Welko Gassage said that putting the Coke bottle effect on the T-38 and the F-5 reduced the aircraft weight by 3,500 pounds because of the drag that allowed you to operate supersonically. Now I have 5 stories I'm going to talk about in the briefing, and 2 of them are here. The first one is at the end of the flight test program, after the aircraft landed, when the crew went to take the magazines out, one magazine was so hot the crew member couldn't touch it. And when Don Murray went back and looked at the data, the temperature had gone up after the aircraft landed. We didn't have the foggiest idea how this thing got hot. There wasn't much flow through the ECS system. We tried to duplicate that in flights, and we couldn't duplicate it. And finally, we went down to the lab in Hawthorne, and we said, well, we'll duplicate the flight. It was the 2 things. One, it was the first flight that we completely ran out of film. Normally, we always had some film left over at the end of the flight. And it was also the first flight that we had a vertical camera and an oblique, split vertical. We had 2 cameras looking at overlapping. And when we ran the film through on the camera and we opened up the camera, there was, let me see, you got it here. There was a clip, steel clip, that had fallen down in a cavity inside the magazine. And this is the core that Kodak winds the film on when we buy the film. And they put the clip on it to hold the film on it when we wind it. Well, when we ran out of film, that clip dropped off. It dropped off in this little cavity, and there were 2 terminals there that had not been insulated, and there were 2 arc marks on it, and the terminals were for the temperature control system. It completely shorted out the system and turned the camera magazine heaters on full blast and completely fried the film. So it's always the unknown things and the small things that get you. Now, the other thing, I was in Norway in 1970 and supporting a NATO competition, and I was at their base in Rygge outside of Oslo. And they had a plaque on the wall with a pilot's name on it. And it was sort of a cartoon, and I said, this is really unusual, what's the deal on this? And they said, well, this pilot was coming back from a mission in a snowstorm. And he had tried to go to an alternate and couldn't get in, and so he was coming back to Rygge. And he had a missed approach and went around, and he had one last attempt to get in, and there was a break enough so he got down on the ground. So the tower called him after he was on the ground and said, why don't you clear the runway? And he said, well, I got the power all the way up. And he said, I'm just taxiing down the runway very slowly. And so they got some binoculars on him and looked down. He landed on 3 tanks in the snow. And he was just sliding along the snow with the power on the engine. So they went out and jacked up the aircraft, lowered the gear, towed it in, did a hard landing inspection, couldn't find any damage, and the aircraft flew a few days later. But they would not let this pilot forget that he landed with the gear up. So. Here's a forward oblique of a B-52 at Edwards. And on the right side is the vertical shot as you passed over the target, and you can see the shadow of the RF-5A on the deck. Now, this picture was taken of Palos Verdes in 1969, high altitude. There's a lot of empty spaces there. When you look at Silver Spur, where all the shops are, it's completely empty. The only thing, one of the few buildings there is the Red Onion, if any one of you know the Red Onion restaurant. And also off to the left, that blank area which was Northrop Space Labs, which is all very expensive houses now, but it was a Northrop facility that was sold off later. Here's a picture of the Queen Mary and the Navy shipyard with an aircraft carrier in the back. And you notice to the left there's no Spruce Goose building. This is before the Spruce Goose was put in for display. This is very unusual. This is an RF-5 shot taken of 5 F-5As coming back from England from a weapons demonstration going back to Williams. And the guy that took the picture said, gee, if I really wanted to, I could become an instant ace. We took the aircraft to Paris in 1969, and here's some of the aircraft on display. They wouldn't let us do any flights during the display, but these were taken when they came in on the approach. Now, here's the third story. We had a lot of problems with this camera, and it was frustrating because it was all controlled by the Air Force. When we started our lab tests, the first camera wouldn't even run one roll of film through. And when we did the tests on the shutter speed, the 4,000th of a second shutter speed was 1/2900th of a second. And the cameras were just not very reliable. We had a full-time rep, and there were a lot of changes made, and it was a quality problem mostly. The design wasn't that bad, and they fixed it. So when we went into flight tests, we had a pretty good reliability in the program. But a year later, after Norway had conducted flights during the first winter, it turned out they had a major problem with the lens quality. It was poor resolution at very low contrast in the wintertime, very low light levels. And the Air Force isolated us from this. They didn't let us know about this for 6 months. And I got a call on Thursday saying, well, we're going to have a big meeting at Wright-Patterson on Tuesday. Can you come back? But he said, you're in a monitor mode only and sit in the back and don't talk. And so, but I did know that there was a low light level condition. And when I looked at our data in the lab tests, we had focused on high contrast targets, which was black and white, because that's what our resolution guarantee was based on. And we really didn't do any tests at low contrast, which is gray and gray. So I went, we still had the lenses and the cameras from flight tests. I went and grabbed those, got some new lenses and cameras from production out of the stock, took them up to the space labs and put the system on optical bench tests. And we did a whole series of tests on Saturday and Sunday. And on the way back, on the flight back on Monday, I put together some handwritten charts as a backup. Walked into the meeting. There were 60 people in this meeting, a whole SPO, standing room only. The SPO director got up and said, well, we're here to review all the data that Maurer has collected from their tests over the last 6 months. And there was a big contingency from Norway. The chief of intelligence for the country, the wing commander, the chief photo interpreter, the pilots, the camera maintenance people, and they even had the military attaché from Washington because this was a big deal to them. The director of marketing for Maurer was the only guy there. He stood up and said, we ran all these tests, came to the conclusion that all the problems were Northrop's aircraft vibration problems, and sat down. And you could just see the full director's mouth drop, thinking, what am I going to do for 2 days? And so I spoke up and I said, sir, I think Northrop has some insight as to what happened. I said, we did some low resolution, low contrast ratio tests, and we found out that the lenses that we had in flight tests performed as expected, and they were very good. But Maurer had substituted a cheap lens in production, and the lens was so bad once you got off axis that the resolution was like 1/3 of what the other two lenses. The other lenses were Zeiss and Schneider lenses, which were very good lenses. So the Air Force went into Maurer, did an audit, found a lot of discrepancies, shut their door, and they went out of business in a year, and they turned over all the manufacturing to another company. and then they went and provided new lenses to the customers. Here's a picture of the NATO competition in Denmark that Norway was in. They had an air bubble building that blew up. They put on a C-130. They had their processing vans and interpretation vans inside, and they could do all the processing inside. They could move it anywhere their NATO commitment required. Watching this competition was like watching Indy 500 pit crew. They were timed on everything they did. From the time they opened, the minute they started opening the nose to take out the magazines until they got film on the light table for the interpreter was critical. Norway did this in 3 minutes and 30 seconds. They took the film out, they took it in the van, they loaded it in the processor, they ran it through at high speed. They washed it, but they did not dry it, put it on the light table, and the photo interpreter had a very short period of time to provide a verbal report on the targets. The next problem, this is the fourth story. Our CEO, Tom Jones, was close to King Hussein. During one of their meetings, he complained to him about how bad the RF-5E was. And the next day, I was on a flight to Jordan to fix the problem, but not knowing what the problem was. All I knew is they had a problem. So I took a camera and some lenses and new film and new chemicals, thinking, well, I could cover all the possibilities. Got to headquarters and spent 3 days going through all these formalities and drinking coffee and tea and being introduced, and could not look at any of the data. They finally gave me some data to look at, and it was bad. I said, why are you taking pictures of tanks at night or at sunset? And they said, well, these were at 12 noon. So we went out to H5, set up a matrix of tests, used their film, their chemistry, their lenses, and the film that I brought. And the bottom line was everything that was done with our film that I brought was just perfect. And their film was completely, it was just terrible. So we went and processed a brand new roll of film that had not been exposed, and it was all fogged. So they looked into it. They found out that the agent had bought a whole year's supply for Jordan. It all came in on pallets at one time. The customs guy couldn't open anything up, so he x-rayed it all to make sure that there was nothing hidden in the pallets. So it turned out to be a very quick solution. Kodak had film on an airliner in New York in 2 days, and they were operational in a couple of days after that. The CF-5, they had a NATO requirement too to take their aircraft to Europe. They came up with a little different solution. Instead of being dedicated, they made 25 noses that could fit and be interchangeable on all 125 aircraft. And the Vinton camera made in England that they had was like night and day. It was so good compared to our camera. The camera, one of the cameras that we got in flight tests, had 1 million cycles on it, and it was still just churning away like a Singer sewing machine. Picture of the aircraft with the nose, the 3 cameras installed. You could put 4 cameras in just like the others, but this is a 3-camera array. Now, when Saudi bought the aircraft, the commander had some background in reconnaissance, and he wanted a pod with a 40-inch focal length lens. It turned out the camera was out of production. It was very sensitive to vibration, and our analysis showed that if we put a pod on and tried to fly at Mach 0.95, the vibration would kill the resolution. And even if we took the bomb rack hooks off and replaced it with hard fittings and made it non-jettisonable, it was still unacceptable. So we proposed an RF-5E nose, but with a new camera. And Recon Optical had developed a KS-121 concept that was like the KS-87, which was the basic standard camera in the RF-4C. Instead of 5-inch film, it was 70 millimeter. It had high-resolution lenses, it had automatic exposure control internal, it had film vacuum, and forward motion compensation. And when you look at the picture, it looks like a KS-92. It was all interchangeable with the same system. But when we flew it, the performance was really outstanding. Big increase in reliability, never had any shutter problems, never had any camera failures. And when you look at the 6-inch lens, The RF-5A resolution had been 22, and the F-5E Saudi was 56, so it was a marked improvement in capability. Picture of the airplane with the Recce nose on, with the missiles, tanks, and stores. Now, what would happen in Vietnam? If you look at the early reconnaissance in the Air Force, during World War II, they had 12-inch film. They had high-altitude cameras. They would do racetrack pass to cover a whole area and record the imagery. In 1960, with the RF-4C, the Air Force downsized the film to 5-inch and reduced the camera size. But when they got to Vietnam, everything went down on the deck in order to survive. So now you have very high speeds at very low altitudes, very high V/H ratios, need higher shutter speeds, need shorter focal length lenses. So in 1972, the Air Force put out a combat ROC. Now ROC is a required operational capability. And they wanted us to change the RF-5A to put standard 5-inch film cameras in the aircraft. When we looked at this ROC, it really fixed all the problems the Air Force had with the RF-4C in Vietnam. The aircraft could operate at Mach 2, but it could operate at real high speeds at low altitude. But the forward oblique camera on the RF-4C was behind the radome, and it was a chin design that came down. And at the edge of the chin, they had a basic aerodynamic problem in that a local shock wave would stand. And if you were above Mach 0.8, the resolution went to 50% for the cameras behind that shock wave. And so they wanted to be sure that we could operate at high speed on the deck. So the first requirement was 600 knots at 200 feet with high resolution. The next major requirement was to fly at 5,000 feet and do a wide 90-degree coverage for 200 miles. Now, there wasn't any sensor at that time that could do that. And so we first looked at pods, and vibration, still a problem. We adapted the F5F concept of moving the avionics into the right-hand gun bay, keeping one gun. We used 2 KS-116 cameras in the proposal with the idea that they couldn't operate fast enough, but we would alternate the 2 cameras so that every other picture was on one camera, but you had the cycle rate that you needed to be able to get the V/H. And then on the medium altitude requirement, we would run one camera until it ran out of film, and then run the other one to meet the 200-mile distance. Now, I ended up going to Vietnam just before the fall in July of '74, and I was helping a large team from the Pentagon that was trying to decide what to do for the whole country. We were in the intelligence headquarters at Tan Son Nhut, and there was some imagery on the light table that came, and there was only one camera around that could do that imagery, and it was an RF-4C camera. And when looking at it, it was pictures of a highway north of Saigon. And the highway was running north and south, and it was a 2-lane road. And it looked like the San Diego freeway at 5 o'clock. Both lanes were filled with trucks and armored vehicles and personnel carriers, bumper to bumper, coming south. And so I turned to the wing commander, the Vietnamese wing commander, and I said, well, these were taken 2 days ago. I said, where's your strike photos? And he says, oh, he says, we don't go up there. He says, we go up there, we get shot down. This was an area called Ben Cat. It was 31 miles north of Saigon, and you could see the handwriting on the wall. They had all this material coming down, and they weren't stopping it. In January of '75, 2 F-5s were hit with new SAM-7 missiles. Both missiles hit on the right-hand engine and blew that out, and also blew the right-hand horizontal off. Both aircraft returned to base with the left horizontal and the left engine, which was really a credit to the design of the aircraft. Now, what this did, this really changed our concept to say, well, even though there was a big focus on low altitude, we better think about standoff imagery, because if we're going to do something for the future, you probably are not going to survive at 200 feet. And we looked at creating a configuration that would allow the pilot to make one single pass. You could probably do that in a surprise mode, But if you come back to try to get the adjacent area, they're going to be waiting for you. So we shifted from the standard reconnaissance to look at the standoff and remote capability, and also trying to add a lot of flexibility. When you add cameras with longer and longer focal lengths, it's like looking through a telescope. Yes, you see more detail, but you're looking through a straw. So to try to find that information is very difficult. Imagine driving down the highway with a pair of binoculars on at 100 miles an hour and trying to find targets on the side. The imagery is just going by so fast you can't do anything. So our solution was to put a prism in front of these long lenses, scan the prism, rotate it so you could go from horizon to horizon, pull the imagery through the camera, and record the imagery. And you'll see some over here, some of the negatives that we did on that wall. So the result was we got the advantage of large imagery, but we got also the large coverage so we could do one pass. Now in starting up the RF-5, Greece came out with a requirement in '74. We briefed that. They had a C requirement. We substituted the RF-5H for the F-5E because the forward fuselages were identical, and this became our baseline for the RF-5E design. President Carter, when he came on board, he said, made a declaration, we're not going to be the arms dealer of the world, and you industry, if you want to export anything, you have to do it on your own, and you have to develop it on your own. We're not going to pay for it. But the dilemma we had was, with ITAR regulations and all weapon systems having to have DoD approval, they really controlled what you could and could not do. And also the regulations, the Air Force said you can't treat your program like a commercial program. You can't fund a development and then amortize the costs over multiple country buys. And so we went back to them and requested approval to do that. It took 2 years to get that approval, but which laid the groundwork to start the RF-5 program, but it also laid the foundation to fund the F-20. The business plan was, with 100 aircraft plus out there of RF-5As, we felt that 50 aircraft was reasonable, and we priced the effort on that, amortizing the development over 50 aircraft. And the decision was made by Northrop to do that. There was one other issue. All weapons aircraft certification has to be done by the Air Force. So on a different turnaround, Northrop funded the Air Force at Wright-Patterson to do an engineering review of all the data, monitor the flight test program, and give us flight certification. The minute we got that approval, we started the demo in March of '78, leased an aircraft from the Air Force. The team was led by Will Thiebel. The program manager was Dr. Len Fowle. And 10 months later, George Myers did the first flight. That was design, fabrication, modification, all the lab tests and everything in 10 months, which was really a remarkable effort. We then flew the aircraft for 3 years with flight testing and customer evaluations. The key to this demo was 2 cameras, the K95 and K93. All of these have multiple selections that the pilot can make in flight. The K95 has a 12-inch lens with 190-degree coverage. The negative is 40 inches long and 4.5 inches wide. It can cycle 0.8 of a cycle per second, and so that's 40 inches a second of film going through, synchronized with the rotation of the prism. The K93 had 145-degree coverage, and this negative is 60 inches long by 4.5 inches. This really allowed a single pass type mission and a large area coverage. Now we scheduled one flight over the South Bay. We flew from PV to Beverly Hills, and we took 65 negatives. And each negative could be viewed in stereo in depth, and we covered everything from the coastline to the Long Beach Freeway. This picture up here is a 4 times blow up. If it was the full frame, it would be 20 feet high, but it's only 1/3 of the frame, and the reason I have it is it's got my house on it. And it shows the radome on the top that you see at the top of the hill, and it looks east down to Miralles School into San Pedro and the Vincent Thomas Bridge. None of the shipping containers are there at this time, but but it shows you the quality that you have, and usually the only way to see the maximum quality is look at the negative. Once you make a print, you lose a lot. But it really demonstrated the capability of the aircraft. Here are the 6 scans. The pilot coming up to a car target can either overfly the target if he feels it's safe. He can turn right and look left oblique, or he can turn left and look right oblique, so he has a lot of flexibility on his mission. Picture of the demo over PV with George Myers. Here's a bottom view of the aircraft. It shows the forward oblique camera, it shows 2 V windows, and then it shows a little slit, which is an open door for the IR lens scanner. The technology at this time did not allow you to have a window for infrared systems. And then there's another window behind it for a viewfinder so the pilot can see directly what's underneath the aircraft. Profile view, and the nose was like Swiss cheese. The structural engineers trying to design this for fatigue life had a real challenge, but we felt you needed to have real quick access to the magazines. You had to be able to change systems quickly, and so that was a lot of focus on maintainability and keeping costs down. Full-scale development. Malaysia signed a letter of offer of approval in December of '80. Northrop kicked the program on in 1981. Recon sensors were done by Bob Walkie. I was the project engineer, and Len Pfau was their program manager. And the first flight was done a month ahead of schedule in December of '82 with Darrell Cornell. And the flight testing was completed in '83. The Saudi program started in '84, and the LORAP system stopped in '86. This is kind of a busy chart, but it shows the whole design approach. We started out with a very good F-5E. We tried to maximize the commonality with the RF-5 with the large sensors, but still retain the weapons. We had a single cockpit instead of a dual cockpit that was in the RF-4, but we had automatic operation and a lot of flexibility with the pilots and the mission in order to provide day-to-day, horizon-to-horizon, standoff, supersonic reconnaissance, all with internal sensors and with a video viewfinder and both visible and IR spectrums and a combat map and then growth for future sensors. The nose was 8.5 inches longer with a 26 cubic foot sensor bay, and then the F5F right-hand avionics bay design and the F5F horizontal for CG control. The RF fell halfway in between the E and the F profile, which was to minimize the risk of high angle of attack. We had a lot of high angle of attack issues with the F5F that we wanted to be sure to stay away from. This shows a comparison of the RF-5A mock-up from the 60s to the RF-5E mock-up in the mid-70s. The sensor system, fairly straightforward. The LN-33 provided the V input, the velocity for the basic equation. The radar altimeter provided the H, all into a central mission computer, and dual cockpit controls and viewfinder and temperature control. We monitored the temperature of the ground on the ground of the cameras overnight, and whatever that stabilized temperature was, we set the temperature control of that to try to keep that temperature in flight to minimize the temperature gradients. And then a vacuum system for the film. All the cameras had vacuum backs to reduce the effect of distortion on the resolution. And then 6 basic sensors with 7 different lenses. So here are the 4 key palettes. Palette 1 with the day, low altitude, medium altitude, and combat mapping. The palette 2 was a high altitude pan and a low altitude pan, so you could go either way. You could either do the mission high altitude or go low altitude. And then the LORAP system. And you look at the LORAP, the palette is just a picture frame. It's very lightweight. The dolly allowed us to move, just completely set up the cameras in the shop, do a checkout, and then roll it out the aircraft and put it in quickly. The 3 view of the aircraft, the cockpit. As a backup to the automatic system, we put a head-up display that gave the pilot time, speed, and heading, so that if he wanted to manually plan a mission, if he saw a target of opportunity, he could go and do that mission without the system being automatic. To support the backup, to prevent having to come back and redo it. Right-hand avionics bay, and then all the compartments open. It was winter time where the rollout became an unveiling inside the hangar. There were 50 key contributors to the RF-5 program. The aircraft flew up a month ahead of schedule and went cleanly and no problems. Picture from the first flight with the Malaysia paint scheme. This is a close-up of the pallet one. And you see the door in the background. There's two windows, and then there's the door mechanism for the IR-line scanners at the aft bay. And then when you go to the combat map, you take that out and replace it with a window for the third camera. And then the 24-inch K93 pallet 2. And then this was the lift dolly. It was just like a transmission jack to allow you to easily load the pallet up into the aircraft. And this view shows the V nose that Roy's going to talk about on high angle of attack, and the pallet being loaded. Now the challenges that we had, one, temperature control is always a gotcha, especially with long focal length lens, so we paid a lot of attention to that. But probably the biggest challenge was we put the IR-line scanner door in. Since there was no window, we had to open up a door. And we had to open it up in Mach 0.95. The door is V, and you're flying at some angle of attack, so you end up actually with a scoop. You're like a big inlet in the front of the nose. And so a lot of emphasis placed on how we design that door to minimize the acoustics of the open door, but also don't destroy the temperature in the bay with the flow going by. And the aero engineers that did this did an outstanding job. We did one flight, it worked perfect, and we never even thought about it after that. The configuration of the door was just outstanding. The second one was putting the LOROP camera, 760 pounds in the front of the nose, affected the CG, affected the structural loads, fatigue, and we did that with a lot of help from Recon Optical. Normally, we would have put the K95 at the back of the bay because it was the biggest camera, but we had to have this door behind the other sensors, so the K95 had to go in the front, and we didn't have enough room. So what they did was they folded the magazine 90 degrees to get it down high enough to fit in the bay. They did that design, and it worked out very good. But the big challenge was Recon Optical took a 15-foot long telescope. They folded the optics 180 degrees so it would fit in the camera bay for the 147. The other one was the quick access doors, the Swiss cheese structure from a fatigue standpoint. And then we wanted to have good access to the forward oblique camera, and so we came up with a quick disconnect for the pedostatic. There was a big safety concern. Well, gee, once you break that, then you got to go do an airspeed calibration test. And so we did a lot of tests to prove that we could do that without impacting the safety of the aircraft. The RF-5E flight testing, all done at Edwards. The Air Force oversaw everything that we did. Complete system evaluated. All sensor resolution guarantees were met, 98 flights, and 75,000 feet of film. The resolution requirements set up by the Air Force was 25 to 35. We actually achieved 30 to 60. The K95 had a new state-of-the-art lens in it. It was outstanding resolution throughout the whole image of the lens. Now this 60 lines was 80% of all the data. When you look at 50% of the data, it was 70. When you look at the maximum, it was 120. We hadn't even seen any imagery of 120 line pairs per millimeter. So the system worked much better, and the platform was exceptionally good. Here's a forward oblique of Mojave, 500 feet, 580 knots. This is a picture of the Northrop ramp at Edwards. The F-20 is on the left and the F-5F on the right. And the next picture is the IR line scanner. The gray F-20 shows up hot temperature on the IR line scanner. The white F-5F shows up cool. But over above that is the aircraft took over off an hour ago. There's a signature on the concrete. The temperature of the concrete is still different than the surrounding temperature an hour after the aircraft took off. And that's one of the values of this sensor, is you could see what's been there and what moved. And every once in a while, looking at the film, you have a surprise. Flight test crew got together and went out and formed an N in front of the hangar, and looking at the film, it popped up on the imagery. This is a Malaysia aircraft over Long Beach, and looking right below the nose, the Spruce Goose building is there. So progress at but the Navy shipyard is still there. Forward oblique. Very seldom see a picture like this. This is taken with a periscope from a Learjet, and really a great shot of the aircraft. Plan view of the aircraft over LA. The next thing that happened, the Air Force said, well, if this aircraft's going to Malaysia, you've got to test this aircraft before it leaves the country in a humid environment. And the only place that was close was England. And so they approved us going down there with the idea that we would test the cameras in the humidity and test the windows for defog, and we would take pictures of military targets. We had a team of 20 employees that went down. Roy flew 10 flights. It wasn't that humid, but we did have some defog, and we had some film stick because of humidity. But our priority was like 272. We never even saw the military target range. We were always modifying our test plan. But the Air Force accepted that, and they bought off on the testing meeting all the requirements. Here's a picture for the night flight that we had. Here's the ramp at Eglin. Here's the crew. Roy's in the center. Bob Walkie and I are over on the side of the nose. And the local Eglin Air Force Base newspaper gave us front page coverage. They gave us credit for the activity that we were trying to do, and gave us a nice write-up. So now, 1984, I got a call from corporate on Thursday, and we said there's going to be a big light show at the closing ceremony of the Olympics Saturday night, and we want you to fly over it with the RF-5 and take a bunch of pictures of the night show. And I said, well, first of all, our night sensor's low altitude. They aren't going to let us fly over the Coliseum at a couple of thousand feet. And two, these are reconnaissance cameras. They're not video. They don't take imagery of fireworks and displays. So I said, if you wanted to do it, let us do it in the daytime and do it at noon, and do it at medium altitude where there's not a big issue, which we did. Roy flew it, took pictures at 7,500 feet. We processed the film that night. We made up a poster. On Sunday, we printed a bunch of copies, and when the engineers came into the tech center Monday morning, we handed every engineer a poster, and you see that over on the wall. It's got a picture taken from the chase airplane of the RF over the Coliseum, and then a picture from the aircraft of the Coliseum. The Saudi program was a major program to us. They flew the demo in 1979. The King set up a special team to evaluate the total intelligence requirements for the kingdom. They ended up selecting the RF-5 in 1983, 10 aircraft with the Pallet 3 long-range oblique photography system, and in-flight refueling testing. And we finished the testing in '86. And they also procured portable vans for their C-130s that they could take their processing vans and their photo interpretation to any spot in the kingdom. Now, the design was basically a RF-5E with in-flight refueling with the LOROP 3 pallet. The LOROP required side oblique windows, and that door replaced the V-door interchangeable. We also set up a preconditioner with the idea that we would precondition the camera to the temperature that we expected the camera to be at altitude on the next mission, and then try to maintain that. We knew we were fighting a losing battle, but we were trying to delay the temperature gradient kicking in, which would reduce the resolution. Here's a picture of the Saudi aircraft, the basic aircraft, the LOROP aircraft with Roy in the cockpit, showing the three-sided door and the camera. The LOROP could look left or right, selected by the pilot, and 3 different scan modes, depending on how much area you wanted to cover. The long telescope from the 146 was bent 180 degrees. There's 2 reflecting mirrors in the front end of it that reflect at 45 degrees. And the lens on this camera, just the glass, was 260 pounds, and it was probably the highest resolution lens that ever went through Wright-Patterson. So it was an extremely good system. The resolution range had no oblique targets, so Northrop set up their own targets, and we did so at the top of a mountain. And this is Laura Mountain near China Lake. We went into the Air Force when the Saudis bought this, saying that we will guarantee 40 line pairs per millimeter because that's what you're doing in the U-2. And they said, no, you're going to do 70. I said, we can't do 70. I said, that's a huge jump from what anybody else has done in the industry. And they said, well, but you have automatic 3-axis stabilization, and you have a very high-performing lens. and you have to do this 80% of the time. And I said, okay, if you let us pick the range and you let us pick the altitude, we'll do that. We had 26 flights. We had a lot of temperature problems at the beginning, and Bob Walke was responsible for solving that and ending up with a good system. And the final resolution that we got 80% of the time was 78 line pairs per millimeter. Like all pictures taken at long ranges, if it's a hazy, foggy day, you're not going to see very far. So it's dependent on the quality of the atmosphere. Here's a picture of China Lake from 40,000 feet at 37 miles away. We did one flight from Santa Barbara to San Diego doing the coastline, which Roy flew. This is a four-sequence photo. At the top photo, the manufacturing plant at Palmdale, which is 65 miles away, is in the top photo. The Edwards ramp with the C-141 sitting on the ramp was at 85 miles. I had one negative in my file from El Toro. Didn't have the advantage of the Northrop Photo Lab to go process it, so I stuck the negative up on the window, took a picture of it with my digital camera, which is a lot lower resolution than this, and then blew up just that small area, and that's the whole ramp at El Toro, which doesn't exist anymore. So you really have to look at the negatives under a microscope to appreciate this resolution. Now, during Desert Storm, the Saudis were in the middle of this. They had 3 aircraft operating all the time. When Hussein set off the oil fields burning, there was an inversion layer. The smoke came up, the inversion layer created a ceiling, and all the U-2s and the SR-71s and the satellites were all blocked. And so the RF-5E was able to look through holes in the smoke and look long distances and get the image. So Schwarzkopf assigned the aircraft to his headquarters for all his high priority target information. The aircraft performed exceptionally well in the pre-war period, and during the war, the 3 aircraft had at least 400 flights. They didn't record all the flights, but there were 397 recorded. Only 7 missions were canceled due to camera problems, and only 9 missions aborted in flight. So the mission reliability was 94% during that time. And when you look at the whole Saudi RF-5E fleet for 10 years during that time, it was 98%. I was in Saudi talking to the director of intelligence for the RSAF, and he said that in evaluating some of the imagery during Desert Storm, he said they were resolving 1 foot resolution at 50 nautical miles. Now that's 1 foot and 300,000 feet. And that's 90 line pairs per millimeter. So outstanding, real-time tactical performance. Singapore, we sold the rights to Singapore for the aircraft so they could convert 8 of their aircraft to RF-5Es. We had a lot of assets and data, everything went to them, and they finished that in 1993, and they designated the aircraft the RF-5S. This is a picture of the aircraft. Later, they converted 7 aircraft in Taiwan to replace their aging 104 fleet, and they designated the aircraft Tiger Geyser. Here's a picture of one of the aircraft. In the late 90s, 1997, we sold a GPS upgrade to Saudi. We started in January 97. First prototype was done in 11 months, and we had the flight test program in 15 months. And all 9 aircraft were converted in 21 months, so it was a very quick responding program. We installed the standard Air Force SNU 764, which is in the F-15 and F-16, but at Roy's insistence, we maintained all the logic that the pilot used for operating it. He made it the same as the LN-33, so when the pilot transitioned from the LN-33 to the GPS system, it was transparent. We had to do the flight test program in Saudi because Saudi wouldn't let any of the aircraft come back. We did that at Taif, including the mission planning. We had 4 flights. They wouldn't let us have any of the data. We said, well, we needed to show the Air Force to prove what we did. They said no, but the Air Force accepted it. We verified the GPS position accuracy with the ground imagery from the sensor because we were pointing at known survey points on the ground. And then Roy completely shut down the system in flight and did an in-flight alignment using the GPS in-flight to stabilize the INU, which had never been done before on an F5. Now I'm led down back to the last two charts. When we look at the major lesson learned, probably the best thing that ever happened to me was all those problems we had with the RF-5E cameras. It was a great learning experience, but it really focused on the fact that you need to have a good relationship with your supplier, and you need to have that up front, and you need to be working the requirements together. And Recon Optical was an extremely good supporter of the aircraft. They had developed 3 key sensors, the KS-121, the K-95, and the KS-147. And like Northrop on their prototype effort, they had done a lot of this on their own nickel before they made a sale. All of these had excellent reliability and excellent performance. Looking at the RF-5E, the development, the design, the performance, everything we set out to do, we did. The system worked very well. The resolution was exceptional, even supersonically. And the platform was very stable. The resolution we measured on an optical bench in the lab, we demonstrated on some sensors 90% in the air of what we got on the bench. So the system, the aircraft was very stable. We substantiated the standoff and single pass recon. We also had high reliability. All the burn-in tests that we did to make sure this thing was reliable paid off. Low maintenance and safety. And our shift to the lower up concept instead of low altitude stood the test of time and was verified later with Global Hawk. So the deviation from the standard proved to be real world. And as I said before, it was the last production camera aircraft designed. Unfortunately, the 2-year delay that we had in the mid-70s, a lot of the customers' budgets got tightened up, and we did not make very many sales. But for the few aircraft that were done, we performed very well.
Thank you for watching Peninsula Seniors Out and About here at the Western Museum of Flight in Torrance. I'm Betty Wheaton. I'll see you next time.